Hello and welcome to our webinar, How Can I Test My Embedded System During Development? I'm Thomas Schütz, and we will talk about early testing for embedded systems, not only with unit testing, but also with hardware, software integration testing. Before I start, I want to mention you can place your questions in the sidebar. There's a section named Questions or Fragen in German, and I will answer some of the questions afterwards or directly after the webinar. And let's get started. So why do we want to test during development? Let's have a look at the problems of late testing. If you implement something, you usually make a unit test, pure software test. That's pretty early, pretty easy, directly after the implementation. But the problem is the later you test, the more expensive it gets, the more time elapses until you get your results. So for example, an integration test usually is not really done, and the system test is a lot of effort, and so usually it's done very late in the process. So our goal is always to bring most of the tests to the desktop of the developer. So directly after the implementation, not within weeks or months, but within minutes. So we need to learn and test earlier. That's the focus here. Let's have a look at the development process. We have a huge gap in the development process regarding testing. So if you have a look at the typical process for the development of an embedded system, you start probably on an evaluation board, you develop or configure drivers, create some hardware related software components, motor control components, for example, or battery control, or bus related protocols, low-level bus, CAN, LIN, and so on. And on top of that, you will have some software components, pure software components, which have the logic, contain the logic of the application. Usually you integrate everything to an application, and eventually you will go to the real hardware, to the real electronic control unit. Yeah, and the problem is, where do you want to test, or where do you have to test? Usually, in most development environments, the pure software components are tested with unit tests. That's a very cheap and fast way to have a certain test coverage, but it's usually not enough, because you cannot really test, or it's really hard to test things like a motor controller or battery controller, or even drivers with a unit test. You need a little bit more than that. And later in the process, you can have a HIL test, hardware in the loop test, which is usually very expensive, and the system test in the real world system is usually even more expensive and very slow usually. So what we do is we bring the hardware in the loop test to the desktop of the developer and create a hardware software integration test. So the smallest possible hardware in the loop test, if you will. And by doing that, we run the integration test directly on an evaluation board, against an evaluation board, with the real software stack. So it's the software as it is in your application, with all the drivers, with all the motor controllers, and so on, and with the complete application software stack. So that's the basic idea. So what do we really want or need? We want to test what is changed most frequently, and that's your software. Now, if you change probably your hardware setup every couple of weeks, every couple of months, you don't have to test your hardware every time, because it doesn't change very often. But the thing that changes very often is your software. Sometimes hundreds of times a day, depending on the size of your project, on the number of your developers. Even if it's only a couple of times a day, it's still a lot that can go wrong. So what we want is, we want to test every code change of every developer within minutes instead of weeks. You also usually want a full regression test also for unrelated code or unchanged code. Probably know the situation, you change something over there and you produce an error over there. That's because you have a lot of dependencies in embedded systems, and it's sometimes really hard to tell what might be affected. You have shared resources, you have probably a performance problem, and so on and so on. So there are a lot of possibilities to produce errors in other sections of the code than what you changed. So you need a full regression test. Another thing is you want a full test automation to enforce tests. So of course you can test on your desktop, but it's probably a good idea, especially for bigger teams or distributed teams, to have continuous integration. So that every change of every developer on every commit is automatically tested. So you can use continuous integration to do this. And the last thing that you need is you need an automated hardware in the loop test, because you want to test more than pure software units. So why is it so hard to automate tests for embedded systems? Let me give you an example. You have a motor control system, for example, for an oil pump. It's a real world system. One of our customers is developing this kind of system, and it's a safety critical system. So they need to test, for example, the temperature shutdown for all the border values, so all the situations for 300 relevant system states. That's the task. So what did they have before? They had a climate chamber. They placed the complete ECU, the complete control unit with the microcontroller, complete software, all the power electronics, the motor, the pump, and the hydraulic system inside this climate chamber. And then they had some test scripts to lower and raise the temperature and to check whether the motor shutdown worked or not. The problem with this kind of approach is that it's really slow. So it would have taken around 30 days to run all the relevant tests only for this single problem. For the complete application, it would have taken a year or so. So that's not a good approach. And imagine you start the test and suddenly you run out of hydraulic fluid. So you have to open the door, put in more hydraulic fluid, and you close the door. The temperature is up again. So you have to wait another 2 or 3 hours to lower the temperature in this climate chamber. So I guess you get the point. That's really hard to automate, and it's extremely slow. So what we did is we took out the microcontroller and tested the complete software on the microcontroller at the pins of the microcontroller as a black box test. So in order to do that, you need an environment simulation for the relevant system elements. For example, for the motor control software, you need a motor simulator. For the bus protocols, you need the other end to send and receive relevant bus informations over the bus. So, but the big advantage is you can test the complete software stack, including all the drivers, on electrical level, on a signal level, which gives you the possibility to change the environment simulation because the complete environment is simulated. So you really can bring the system in any problematic situation you want to test. By doing this, you can introduce a very, very nice failure injection and basically test whatever you want. In this case, the complete test for the whole system, we brought this down to 50 minutes, completely automated for all the states and all the other situations as well. And that's extremely easy to automate because essentially the environment is just a simulation. Of course, you have to do something for that. So before I explain how we do this, let's have a look at the different test levels and methods. So let's have a look at the same system again. We have the system, and in the microcontroller, we have software running. It's your application software. Single software units you can test very good with a unit test. That's easy to do. There are a lot of frameworks out there that can help you doing that. Please do this. That's a very, very cheap and fast way to have automated tests. If you bring several software units together, it's already a software integration test. You still can use a unit test system or unit test method to test this. It's still pure software. The problem is in the next level, you do not get away with a pure software test, because if you integrate the drivers, if you integrate, for example, a motor controller, bus protocol, and so on, you already need an environment simulation and you need a hardware in the loop system. So what we essentially do is we created the smallest possible hardware in the loop test system. So we are testing the microcontroller as a black box at the pins of the microcontroller. That's a relatively simple setup. And by doing this, we can really automate these tests very good. So the next step would be a big hardware in the loop test, including power electronics, sensors, actuators, and so on. That's already a lot of work. It's a useful test, but it's usually hard to automate, and it's very expensive. And the last step would be a full system test, including the real world, like a motor, a pump, hydraulic system, and so on. That's even more effort, and usually not to automate, or not really good to automate. So the effort is rising from a unit test to a system test, yeah, you also can run a unit test very often. It's inexpensive, and at the lower end here you have the system test, which is usually very slow. You do not execute it very often, and it's extremely expensive. So with the miniHIL, we are somewhere in the middle here. Still very good to automate and relatively simple in comparison to a system test. So let's have a look at the response times for the typical tests. A component test, so a software integration test, for example, or a unit test, is usually in the range of minutes. So you change something, and within a couple of minutes you get a response from your test system. Integration tests, at least the hardware software integration test, usually is not done. System test, either HIL system test or a real system test, usually is run typically in every couple of weeks. That's because it's a lot of effort to do this, and the equipment is really expensive. The acceptance tests are usually on a system test level, so they are also not run very often. So what we do is, with the hardware software integration test, with the miniHIL, we already have a real hardware in the loop test, but we also have response time more like a unit test than like a system test. So it's also in the range of minutes, sometimes a bit more, sometimes a bit less, but you get a very fast response for every change. Here on the right side, you see our miniHIL system, mini hardware in the loop system. I'll get to that a little bit later. So the goal here is to have a very fast turnaround by test automation. So you get a turnaround or response from your test system within a couple of minutes instead of weeks or even months. So we close the testing gap here. So what can you do with the hardware software integration test? So the main goal is not to test a single software component or single software components, but you want to integrate the software components into the software system, including the drivers and even the electrical system signals. Because without the electrical signals, it's really hard to get the drivers into the test system or into the system under test. But once you have this, you can put your system in almost any state to test it. You just need to change the simulation for failure injection. So if you have a real temperature sensor, you need a climate chamber. If you have a simulated temperature sensor, you just need to change an analog signal to change the temperature or any value you want in milliseconds if you want. That's really fast and simple to do. So this enables a complete automation and gives you speed and depth in your test process. Let's have a look at an example. So we regard the microcontroller as a black box. We test at the pins of the microcontroller. So the system under test in this case is a microcontroller with the complete software, application software, and the drivers. And let's have a look at this temperature shutdown example from before. We want to stimulate the temperature sensor. So we need an analog value as an electrical signal, 3.3 or 5 volt. By that, we change this, stimulate the ADC. The ADC now gets the temperature change, and then the events cascade through the system. That's something we do not see from the outside, but we want to see the effects. So, for example, in this case, the error controller communicates the error to the application, to the motor control. And what we really want to know is, for safety critical reasons, does the PWM shut down after 100 microseconds? So you really want to know whether the motor stops or not. We can measure this from the outside. And the other effect we want to see in this case, whether we get the right error message over a CAN bus signal. We can measure this very good from the outside. And by that, really doing a hardware-software integration test. So we want to keep this as simple as possible. That's why we created a hardware and a software platform to really do this work. Here you see the miniHIL hardware platform. On the right side, you see the system under test. So basically, the system under test is just a microcontroller on this standard evaluation board, in this case, an ST. So ST microelectronics microcontroller, Cortex M4, for example. Can be any other microcontroller, it doesn't really matter. The pins of the microcontroller we can connect over this of those wire jumpers with our test system. The test system has GPIOs and so on, but also indirectly other IOs like many ADC, DACs and so analog outputs, digital analog outputs, all the bus systems, the low-level bus systems, and so on and so on. So now we have connected all the signals on our system under test to our test system. On the test system, we need now a software that does three things. First of all, it needs to connect all the low-level signals, the signals, electrical signals, to our test software. The second thing is we need to simulate the environment, like motors, batteries, sensors, and so on. And then on top of that, we need test cases to really test the situations we want to test. We need to test to make sure our system works by testing the good path, the happy path, and also the unhappy path. That's usually the more important path. Okay, so in order to do this, we need to create software. What we have here is a model-based software development approach for the system for the test system. So we simulate, or we develop the simulation and the test models based on a model-based approach. So we model the structure and the behavior of our simulation and the test system or the test cases. Then we generate C code. We flash or we compile this, flash it to our test system. So we're talking about the left side here. And then the test runs on this microcontroller here. It's also a microcontroller in hard real time. So we can simulate motor controllers up to 30, 40 kilohertz, for example, or go down to 100 microseconds for test cases. So not milliseconds, but microseconds. And on the right side, here you have a system under test, in this case, an Oryx, Infineon Oryx processor. And when the test case is done, we collect the protocols, convert them to diagrams. Diagrams are usually better to read for human beings. So high-level diagrams like traceability information, for example, or requirement coverage, or also low-level diagrams like the sequence diagram that tells you exactly what happened in the test case and at which point, for example, a test case failed. Then we learn and iterate, and we continue to modify our system under test or our test system. This usually takes in the range of minutes, so it's a really, really fast process. Let's have a look at the typical test setup on your desktop. So we have the hardware in the loop test system here, the miniHIL. It's connected with your laptop or with your PC. And here you develop the test models, and basically that's the setup on your desktop. I have basically the same setup here. That's here my demo setup here. So I have exactly the setup here on my desktop. I will show you this in a minute. And yeah, that's usually for one project or for one developer on his desktop. If you have more developers, or maybe your developers are distributed all over the world, or you have many developers and you do not want to have a test system for everybody, you can do this also with continuous integration. So every code change of every developer that is changed, you get a reply for also in the range of minutes. You get a very fast feedback by using continuous integration. So we hook up the continuous integration server to the miniHIL boards, more than one. In this case, we have 8 different projects in a rack, so 1 meter high, this rack, and we have 8 projects here. So what the continuous integration server does, every commit is monitored, and every commit, the new software version or also the application, but also the test system is built, is tested, and is potentially delivered. Continuous delivery is a good idea. You should definitely give this a try. It helps a lot. Has nothing to do directly with the miniHIL, but the continuous integration is essential to make continuous delivery afterwards. So the thing is here, you can just test every code change worldwide of every developer for every project within minutes. Where do we use this kind of approach? Basically in all kinds of domains, in automotive, aerospace, medical devices, and so on and so on. So basically everywhere where the typical 16 or 32-bit microcontrollers fit. We also have customers with 8-bit microcontrollers or 64-bit microcontrollers, but everywhere where you have a lot of, let's say, digital, analog, or low-level IOs, low-level bus system, CAN, LIN, motor controller, things like that. Those are very typical systems here. Now I'm going to jump into a little demo. I prepared a little demo system here. Again, you see the system under test and the test system. And here are the wires where I used to connect on an electrical level, 3.3 volt level or 5 volt level. And the system under test contains a motor controller. It's an STM32 Cortex M4 processor. It contains a motor controller for a BLDC motor. This motor controller generates 3 PWMs. They are measured in the test system. The test system with 20-30 kilohertz, for example, calculates the new speed of the simulated motor and generates 3 digital outputs to simulate the Hall signals or analog outputs, for example, for field-oriented control, so that the microcontroller and the motor controller especially really don't know that it's a simulated motor. So we also simulate the temperature sensor as an analog output and the UART to control the motor speed and things like that. So that's the logical structure of the tests of this test setup. Let's have a look at the electrical. Let's have an electrical view on the signals of such a test system. So here, for example, you see the 3 PWMs generated by the system under test. Here you see the Hall signals generated by the test system. And here the UART to control the speed and get the error messages and so on. And here you see the same, a little bit further away, PWMs, Hall signals, UART. And here I added the simulated temperature as an analog value. That's from the test system. And here also from the test system, the simulated speed. So that's just to verify, to get a correlation between what the simulation does and what my system under test does. And now I can run test cases like I can change the speed. For example, here over UART, I change the speed. The motor controller reacts, gets slower. You can see this very good here. And the motor simulations simulates the motor. And here see the Hall signals. So that's what the simulation here, that's the speed of the simulation. Here you see the Hall signals. But it's easier to correlate this to this analog value here. And then we have here a motor stop for temperature shutdown. That's exactly what I mentioned before with this other system. So here the temperature gets too low as an analog value. So the motor control needs to shut down. That's exactly what happens here. The PWM goes to 0. And here that's a real simulation. It's a closed loop simulation. So you see the motor gets slower. The simulated hardware gets slower. Then here you have a warning, limp home functionality. The motor just gets lower when you hit the warning temperature. So, and in the end, the motor recovers again. So it restarts again when the motor temperature goes to a normal range again. So those are on electrical level. That's a view on the typical test cases. So let's have a look at how we do this. I'm doing a little demo. I'm jumping in the development environment for our test models. So everything that's in this box here, in this so-called actor, is generated and flashed on this test system, on this microcontroller. So what we need, I jump into this into the section I need to show you here. What we need is 3 things. We need the IOs, so those are digital, analog, inputs, outputs, UART adapter, the Hall generator, and the duty capture unit for the PWMs. On top of that, we have the components for the simulations. Motor temperature is just an analog output, so we convert a Celsius value into an analog value between 0 and 3.3 volt in this case. And the motor simulator is a real closed loop simulator. You can put in a piece of C code if you want. You can use a generated motor simulation, for example, from MATLAB Simulink or other tools, or you can directly model an event-driven simulation directly in this tool. So for example, in this structure here now I open the behavior. That's a state machine. So if I get a change, for example, from the PWM interface, it's measured. I measure the actual duty cycle and I feed this into the function to calculate the actual speed. And then I inform the Hall generator that I want to set the speed to a new value. So Hall generator, that's the interface to the Hall generator here. I can also set direction. For example, I can change the direction of the motor. This would be an example for a failure injection. If I just change the direction of the motor, the motor controller should react on that and produce an error and stop the system. Yeah, this would be an example for failure injection. And so the behavior here is directly connected with those ports here, with those interfaces to the components that do the actual simulation work or I/O interfaces. So now, when I have those 2 layers, I can already simulate the complete, in this case, the complete system. So my system already would work against the simulated system. But of course, I want test cases on top of that, and the test cases can either directly communicate with the system under test, in this case over UART, or they can communicate over the simulation elements, for example, modify the temperature or make failure injection in the motor simulation, or check whether the motor has actually the right speed. So the test cases also need behavior. So that's where we have this other language here. It's also deeply integrated like the state machines. It's a textual syntax here. And with this language, we can define test cases. Let's start at the Lowest level here, for example, I want to request a new speed. Here I inform over the UART, the system under test, that I want to change the speed. Again, same thing here. That's the interface to the in this case to UART, or I can also interact with the motor control, with the motor simulation, and modify this and get the actual speed or change the direction. So that this would be a failure injection now here. In this case, I just want to change the speed and ask the motor simulation or the in the next step whether the speed has been correct or not. So, for example, on a layer above, I have to set and check speed, and this element puts two steps together. So request speed and check speed into one test case or into one sequence. And here you always see the documentation for the sequence. If I change something here, you see it directly in the generated specification. So it's just a graphical specification for this textual blocks here. And on top of that, we have a test suite. Then, and here you see the complete story for a test suite. So with all the test sequences, steps, test cases, and so on. So that's the expected behavior. So now I have the simulation that really simulates the complete environment. And I have the test cases I use to verify whether my system does what it should or whether it does not what it should, or maybe I can try to break my system with failure injection. Now I generate the code, I flash it to the system under test. That's, you can do it from the graphical user interface. You can do it from command line for continuous integration. I'm using in this case the graphical user interface here. So here I have the system under test. Here the test system. I will modify those wires. I will pull a plug when I start this, and now I'm going to connect to the test system. Now I'm really connected. And now I'm going to start the test run. Here you see the test run. I'm going to pull a plug when the test is running here. Now you see I produce an error. That's usually not what I want to detect, but I can also, of course, detect the software errors. And here you can see that I have actually detected some errors. And if I go down to the error, yeah, that's the. Let's have a look at the real error here. Here are the errors. The first error, that's a timeout error. And if I click on the timeout error now, in the background, my model opens exactly at the position where the test case actually failed. So it failed in the request speed, but I need more context. So that's why you have the whole sequence diagram of the complete test run always. And that's the same diagram as before. So it's the sequence diagram here, but in this case, that's the executed as a sequence diagram, the log from the execution. Okay, so that's now I fixed the problem again. I put in the wire again. That was the UART, I guess. And I'm still connected, so I'm going to run the test case again and check whether it works again. So that would be a full regression test. Here also we have combinatorial tests, and now everything is green, so the test passed. Okay, so that has been the demo. If you have any questions, don't hesitate to contact me.